a second. Where did... There we go. Alrighty, so let's continue kind of where we left off last time. Let's see if I can't fix this silly camera. Kind of better. Okay, anyways. We kind of finished talking about phase change diagrams, in particular heating curves like this, where we had some, measure of heat that we would be giving to this system, and then we had temperature as the other axis. And we saw maybe that we kind of have 2 points on this that are of interest. We have here the boiling point and the melting point on this graph, which correspond with the temperatures at which the solid will melt or the liquid will vaporize. And we kind of discussed that the total energy required for this entire heating curve to happen was going to be equal to the Q's for all of the processes and states that we have there. This is liquid to gas, and then we of course have Q for gas. So, and then we remember we kind of have two formulas here. For whichever one is just in one phase, remember there's always a temperature change that's happening if you apply heat to something that is just one phase. And so we're going to see that that was just our MCAT formula. And then the phase changes have their own energies. Remember that once you reach your boiling point or melting point, all of the energy that you're adding in is going to break up kind of the structure of your substance. So if it's solid going to liquid, it's breaking apart your nice, orderly structure and making it so that now the molecules are flowing around past each other. And if it's from liquid going to gas, you're having liquids kind of free themselves from the other liquid molecules around them from the intermolecular forces there, and so then they're going to jump off into the gas phase. Hi, little dude, you want to go say hi to everyone? Or are you just looking for food? Okay. And so, of course, we just had for that the enthalpy change associated with those. And, of course, you'd use the appropriate one. So with all this fun, equation stuff out there, let's go ahead and take a look at an example. So let's say I have benzene, which is C6H6, and I have, 100 grams of that. And let's go ahead and look up some thermodynamic data. We have its boiling point and melting point here. I'm copying these from Wikipedia, of course, our most favorite source for these sorts of things. And its boiling point is 80.1 degrees. All right, here's a bunch of constants for us. Liquids or solids is 118.4. These are all going to be in joules per mole Kelvin. So I'm not going to put the units for the other ones. We have 134.8 And then for gas, we have 82.44. That's not 82.44, is it? Same units for all of these. Delta H fusion for this is going to be 9.9 kilojoules per mole. And delta H vaporization is going to be 30.77 kilojoules per mole. Okay, we have a ton of data here, tons of numbers to work with. And so let's say we are going from, we're going to heat some benzene up from 0 degrees Celsius. Let's put some sig figs with that. To 100 degrees Celsius. And so let's see if we can find out what is the total amount of heat needed to heat benzene, 100 grams of that, sorry, I meant to put that earlier, from 0 to 100. Exciting. Tons of information here. So let's go ahead and look at that graph that we had drawn earlier. And let's go ahead and put some numbers in here. So I'm just going to erase this right now. This is our temperature, right? So we do see that on this graph there are kind of a couple points we should put in there, and that's going to maybe make it easy for us to see what temperature changes are taking place, so that when we do our MC delta T, that we'll know what our delta T's are. So we have here kind of 4 temperatures, right? We have a melting point, a boiling point, a final temperature, and an initial temperature. And so all of these 4 should go on our graphs. And we're going to see that these are all going to be kind of points that will be important anytime you're doing a heating curve. So let's go ahead, since we've already marked our boiling point and melting point, let's go ahead and put those numbers in. So our melting point 5.53 and boiling point 80.1. Those correspond to where those plateaus are, where we have the slope of 0. Okay, and then let's see, we also have 0 degrees and 100 degrees, and that's kind of the range of what we're looking at in this. So we're going to see that the lowest temperature we're going to look at is 0 degrees, and the highest temperature is going to be 100 degrees. Just because that's what the problem did. If I went from negative 50 to 150, we would just put those numbers instead for the endpoints of our graph. The melting point and boiling point, of course, don't change. So we can just leave those as they are. Okay, cool. So what we can see now from this graph is that we are solid from 0 to 5.53. We are going to be liquid from 5.53 to 80.1 degrees. Right, so we're liquid that entire portion there. And then we are gas from 80.1 to 100 degrees. So do we see how we've come up with all these numbers using this graph and how we've placed them here? So for every substance, of course, is going to have a different melting point, freezing point. So you'll always want to make sure that you know where to put those on a graph. If I said we were stopping at just 50 degrees, we would, we would just end our graph here or something, wherever 50 degrees happens to be, and we would only have 3 Qs to work with. But since I've said 100, we're going to have all 5 Qs here. And there goes our axis and other stuff here. Let's just undo that. Okay, let me erase this very carefully this time. Okay. So really this is just a matter of now plugging things into our formulas. So we now have, for our single state ones, we're going to have our moles. Actually, we have grams, so we'll deal with that in a second. We have our specific heat capacities. Those were given to us. And now we have our delta T's. With the fusion and vaporization, we don't need temperature changes. We already have the delta H's given to us as constants. And so we're going to just need our moles there as well. So remember, M could be mass or moles. It just depends on the units of your heat capacity and delta H. So all of these look to be in units of moles. So we're going to use moles for all of the Q's for this one. So let's go ahead and get that mole ready then. So we have 100 grams. With 4 sig figs, it looks like. Let's go ahead and look up our molar mass because we are lazy and don't want to do it. Don't want to calculate 6 times 12 plus 6. And it looks like this is going to be 78.114 grams for 1 mole. So doing this, 100 divided by 78.114 gives us 1.2802 moles. So we're going to use this number here. Perfect. Excellent. I'm just going to leave it with 5 sig figs just to carry that over and not round it quite away just yet. Okay, so now let's go ahead and do all this stuff. So we have 5 Q's to deal with, right? So we can just start from solid and go all the way to gas. So this is going to be equal to the specific heat of the solid times the, I guess I'll be consistent with my order. We had M first for with our specific heat for the solid as well as our temperature change for the solid. And so that's going to be 1.2802 moles. We have our 118.4 is our specific heat. Remember, for specific heat capacity, mole or Kelvin and Celsius are identical because these talk about changes in temperature. And a change in Celsius is exactly the same as a change in Kelvin. So we can leave it as Kelvin. We can just change it to Celsius. That's not a problem. So let's go ahead and find our change in temperature. It looks like that's going to be 5.53 degrees. It's 5.53 minus 0. So we'll leave it as 5.53. And you know what? I'm just going to go ahead and make our specific heat in degrees Celsius just so it's a little bit easier. Again, either one, keep it as Kelvin, doesn't matter. But remember, only change before you subtract. So again, you're just adding extra work to yourself. So just change your unit, make it easy. Okay, so moles cancels. Degrees Celsius cancels, so we have joules left over. So Kevin is going to calculate that for us. He's already done it. That's awesome. 838.2 joules. All right, so now we're going to do our solid to liquid transition. So that's M times delta H fusion, which is going to be 9.9 times our 1.28. So this time we're going to be left with units of kilojoules, which let's just go ahead and convert them to joules. So 1.2802 times 9.9 gives us that many joules. So you'll get 12.67 kilojoules, but I'm just going to leave it in joules right now, just because since we're going to have to add these all at the end, it'll be easier if they're all in the same unit. Looking at this, we have really only 2 sig figs. Okay, well, we'll remember that. All right, and the rest, again, is much the same. C for liquid times delta T for liquid. So that'll be 1.2802 1.2802 moles. Let's go ahead and look up our specific heat. It was 134.8. And then our change in temperature is 80.1 minus 5.53. So remember, delta is always final minus initial. So that is going to be minus 5.53, 74.57 degrees Celsius or Kelvin. That's our change in temperature. We can do the math. 1.2802 times 134.8. This one we get 12,869 joules. Again, all of our units should cancel out except for the joules. This is nice and tedious, isn't it? We get to do so many of these fun things. So the only kind of stuff that's new here is putting it together, I guess. I mean, we've kind of, or actually, no, I don't even know. This is really much the same as other stuff we've done. So now liquid to gas. 1.2802. These delta H vaporization 30.77. .28 times 30.77 is 39,392 joules. Okay, and now we have the last one, Q for gas. Thank goodness we're almost done here. .2802. Our specific heat was 82.44. And then our temperature change was 100 minus 80.1. Oh gosh. Well, that's 19.9. I just have no room. There's the one down there. 82.44, 19.9. Doing this, you get 2100 joules. Woo, how exciting. All that fun stuff. Let's throw in our sig figs, by the way. We have 4, 4, 4. And this one was already in. Should be 3 for this one. Okay. Ooh, how exciting. Let's add all this stuff up now. So, sorry, 838.2. I'm going to need to move that. I realize that's a small number. Okay. 12,674. 12,869. 393.92. And then 2100. Oh, how exciting. Let's add all this up. 830. This is really, I guess, at this point, just a sig fig problem, isn't it? 12,674 plus 12,869 plus 39392 plus 2100. Adding this all up, we get 67873.2. And it looks like we're going to want to cut our number off over here. And so we should round this to 68,000 joules or 68 kilojoules. Awesome. Even with sig figs. Very nice, Kevin. Woo, we did all that work for some reason. So there we go. Just so we know, if this were the opposite process, if we cooled 100 grams of benzene from 100 to 0 degrees Celsius, the Q would just be negative 68 kilojoules. So that's the only difference. Yeah, exactly. It's exact same number, but just negative. So you're going to see that your delta T's would all be negative, and for delta H, you would just switch the sign, because if you're evaporating something that's endothermic, it should be positive. But if you're condensing, that is exothermic, so you make your delta H negative. But the number was the same. So, for example, delta H vaporization is what, 30.77 kilojoules per mole. You would keep this as positive for boiling, but you would make it negative for condensing. So it just depends which way you're going. So if you're going from gas to liquid, you make your delta H negative. If you're going from liquid to gas, you keep your delta H as positive. So, yeah, there we go. How exciting. Okay, you'll probably just have like a homework problem like that. Obviously, this is way too long to do on an exam. I mean, that took us, 20 minutes to do just this 15 different calculations. So, yeah, there we go. Cool. Any questions on that one? I'll just put the numbers here. Okay. So that's the only difference. So if the thing is cooling, you can actually just do the whole process as if it were heating and then just throw the negative at the end, whatever way you like to do it. So if you like dealing with all negative numbers or all positive numbers, whatevs. All right. So let's go ahead and talk about phase diagrams then. So we're going to see these relate pressure and temperature to state of matter. So we know that the closer things are, closely packed together molecules or atoms are solids, kind of intermediate where they're still kind of close together but flowing past each other, those are liquids, and then far apart we have gases, right? And we kind of have two ways to mess with that. If we have high pressure, we can force molecules to get close together just because, they're being hit with, gases or whatever the pressure is being caused by, to force them to get close together, to compress them. And that's going to make things more like a solid, right? And we also know that temperature is required to break the intermolecular forces between things. And the more temperature you have, the more energy you have to break free of intermolecular forces and go off and be a gas and zip around, do your own thing. So typically these are done with temperature on one axis, and you have pressure on the other axis. We can say go ahead, put degrees Celsius and atmospheres here. Just so we know, for a phase diagram, the pressure axis is usually logarithmic. So that means, you might have one atmosphere here. This would be 0.1, 0.01, 0.001. It's logarithmic. So instead of just 1 through whatever, you go by tens. Okay, and then temperature, of course, maybe we have, 0 degrees Celsius here. Here's negative 100, negative 200, 100, 200, 300, whatever. Just to give you an idea of what these typically look like. So what you'll see is that often you'll have something that kind of looks like this. Maybe this is too broad of one there. Let's go a little bit more like this. Yeah, that's better. And so you'll see that you are going to be a solid here. You're going to be a liquid here. And a gas here. So this is just a generic, indeed, we're going to have triple points. So this is a very important diagram for people who are doing engineering with any sort of material, because you're going to see that if you manipulate the temperature and pressure, you can get something to go into a particular state of matter. And as Shane has already pointed out, there's a couple of interesting points on this graph that we're going to want to look at. There is that one there, and then there's also the one in green we're going to put over here. All right, so the purple dot is the triple point. And so that is kind of the magical temperature and pressure at which all three states of matter are in equilibrium. So that means your substance is rapidly changing between gas, liquid, solid all at once. So it's a very interesting temperature to look at. So and pressure. So it's where you have all three states at once. What's particularly perhaps more interesting is the critical point. Typically, this is the temperature at which pressure cannot force a liquid to form. So this is technically the definition for the critical temperature, but the point is where that temperature and pressure meet. So you're going to see that at a certain point, this graph, or this point between liquid and solid will just keep on going forever. However, the one that ends in the critical point does not have, or it has a finite end, and that is the critical point. So we're going to see here we have what is called a supercritical fluid. So super meaning, above, or, actually above is a pretty good place. So above the critical point, you have, you're going to be in the state of what is called a supercritical fluid. And that is something that has kind of intermediate properties between liquids and gases. So it's going to, actually there's a pretty cool, let's see, I think YouTube had a pretty good example of one. Let's go ahead and take a look. Let's see. Okay, yeah, let's watch this video.
This year,
no, we have ads. How awful. Okay. Okay, let's go ahead and skip these silly ads. No, I do not want YouTube Premium. So, looks like we have gaseous CO2 in here. And this guy's apparently gonna just go crazy with the clamps and the pressure and all that fun stuff. Let's see. Boring. I don't know, do we have supercritical stuff at this point? No, he's fixing his thing. Aha! So there we go. So, we can see here that this supercritical fluid kind of looks like a liquid. Or this might actually be liquid phase. I guess we should put on this.
But I designed this chamber thinking that I would actually encounter anticipating much higher pressures.
Oh, this guy never shuts up.
And then turn the heater on and off and monitor the temperature and pressure. So I got it up to...
Aha. So, okay. So we saw that we kind of have this line here where the liquid is. You can kind of see it. And he's apparently increasing the temperature on this. And as we scroll up, we see that line kind of disappear. So we can no longer kind of see that kind of liquid gas interface there. We kind of just have one kind of a solution, not a solution, it's one substance. It's a, now completely uniform thing in there. And we're going to see that it has properties of both liquids and gases. Let's see.
To see if the pressure is going to be higher. Supercritical CO2. The first thing I want to try is putting green coffee beans in there and see if I can extract the caffeine from them.
He's doing some
One of the
crazy
commercial
stuff.
uses of this process is to decaffeinate coffee beans, but of course the
This is
caffeine
true.
doesn't get destroyed. It just
Let's
oily
see.
substance on it, carbon. So
Okay, well, whatever. You guys can look at this YouTube video if you really want to see it in detail there. It was longer than I anticipated. Otherwise, I would have shown the whole thing. But the point is, supercritical fluids are kind of intermediate between liquids and gases, and they have some very cool properties. Like he said, you can use supercritical carbon dioxide, which actually becomes supercritical at... Yeah. So you can remove caffeine this way. So because it acts like a gas and a liquid, the gas-like behavior can permeate the coffee beans. And so caffeine is a pretty non-polar molecule. And so it will actually dissolve in that supercritical fluid. And then you can just extract the CO2 out, blow it out, and poof, you no longer have caffeine in there. Which is pretty awesome. It's also used to separate things in the drug industry. So when they're, synthesizing drugs, this is a very effective way to purify that particular drug so that you don't have byproducts in there as well that may have, toxic effects. So, there's a lot of interesting, like, kind of engineering things you can do with supercritical fluids. But for right now, just understand they have properties intermediate between liquids and gases. So they are gas-like, but they have very close together molecules, so they still kind of behave like liquids. Cool. And so the utility of these is you can kind of look at a particular substance's phase diagram, and you can use it to kind of predict at what conditions what state of matter it will be in. So we also have a couple of other points on this that we've seen before. Typically, we talk about melting point and boiling point at 1 atmosphere. So if we were to trace this along here, we would see that this temperature, this would be our melting point on that graph. And if we were to continue to where it turns into a gas at 1 atmosphere, that would be our boiling point. So we can see, depends. So plasmas happen when you start ionizing things. The temperatures required to do that would be extremely high. So, I mean, you would probably need to use a plasma to get it to form a plasma, for all the sense that that makes. But presumably, yeah, if you gave it enough energy to start stripping electrons away, then yeah, you would get a plasma at the end of that. But the idea here is kind of more... No, I think I'll leave it at that. Yeah, so eventually, yes, you could get a plasma if you kept heating it up. You could do that with just a gas as well. So if, you just kept heating the gas at low pressure, you could get a plasma that way as well. So yeah. These curves on this are not, identical for each substance. For example, water has one that actually this kind of bends. I'll just put waters kind of here. Waters somewhat actually kind of goes backwards a little bit, and maybe something like this. This is what waters look like. Water looks like. So different substances have different looking graphs, but all the points are still there. So you would still have your triple point, your critical point, your melting point, and your boiling point on all of these things. So there we go. One more kind of thing to note is that the more intermolecular forces you have, the higher your critical point is. So something like water, we're going to expect a much higher critical point than we would for something like carbon dioxide. Carbon dioxide is nonpolar. It has a relatively low critical point. Let's go ahead and look it up. Let's see. CO2 critical point. So its critical temperature for CO2 is, let's just look at some numbers here. CO2 is apparently 31 degrees Celsius, which is an awesomely low temperature, and 72.8 atmospheres. That's when CO2 becomes a supercritical fluid. And then how about water critical point? Let's look this one up. So for water, we're looking at 374 degrees Celsius and 218 atmospheres. So we can see a pretty big difference here, right? We have water that is roughly double the temperature of the carbon dioxide and triple the pressure. So, by the way, I'm doing double from a Kelvin type of scale. So this is, roughly almost 600 Kelvin. This is about 300 Kelvin, so twice as much temperature and 3 times as much pressure for water. So if you were to kind of be given a question to say which one would you expect to have the higher critical temperature or critical pressure, you would go with the one that has the strongest intermolecular forces. Exciting. Nope, critical point is 1 point. So it is the temperature and pressure at which that change happens. So if we look at a graph like this, if we change our temperature or pressure, we would be going away from it. So if we were to lower the temperature, we would be a liquid. If we were to lower the pressure, we would be a gas. If we were to increase the pressure, we would still be a liquid. If we were to increase the temperature, we would still be a gas. We're going to just kind of assume this goes well here. Let me show you a prettier graph. Yeah, this will work. Okay. If we look at this one, we can see kind of at that critical point, if we mess with the temperature, say we're still just below the critical point, and we increase the temperature, we're still going to be a gas. So we're in the gas phase down here. If we were to lower the temperature at the same pressure, we would be a liquid still. If we increase the pressure, we're still going to be a liquid. If we decrease the pressure, we're still going to be a gas. So we have to hit both of those marks to be able to be a supercritical fluid. So you have to increase both of them. Yeah, that's the point there. So yeah, this is a much prettier graph than something I can do, of course. So there we go. Thank goodness for Google. This makes it actually a lot easier to teach this sort of stuff when we have diagrams and, nicely drawn molecules for me. I don't have to do it myself. So point is, though, the critical point is kind of dependent on your intermolecular forces. So the more forces you have, the higher your critical point is going to be. All right, let's talk about another thing. Vapor pressure. So here is our container. Let's put some liquid in there. What liquid do we want to use? We could use water, whatever liquid we want. If we were to just put water into a completely vacuumed vessel, we're going to see that some of that water is going to vaporize. So if we remember back when we talked about temperature, remember we talked about temperature being, kind of the average kinetic energy. If we just take a look at this, I'm going to just kind of arbitrarily draw a line here. And I'm going to say that this portion of molecules, these have enough. Remember, this is energy and proportion. These have enough energy to become gases. So, you're always going to have some small portion of your molecules at any given temperature that will have enough energy to become a gas. And so we're going to see that if we were to put water into an empty, a vacuumed container, we're going to see that a portion of it will immediately kind of just turn into a gas, just because that portion of molecules happens to have enough energy to do so. We're going to see that we're going to have basically molecules that are kind of switching places. So eventually, these molecules will slow down enough that they're going to condense back into a liquid, and we're going to have parts of that liquid that are going to get enough energy to then become a gas. So we call this a dynamic equilibrium. So you have, molecules that are in the liquid water that are jumping out. You have molecules in the gas phase that are condensing and becoming liquid again. So you have this process just kind of happening back and forth. And we're going to see here that the pressure exerted by the gas is called the vapor pressure. So again, we have a vacuum here. So there's nothing in there. We have somehow gotten our water in with nothing else in there. Immediately we get some molecules popping out into the gas phase. Gases exert pressures, as we've studied, and that pressure is called the vapor pressure. And that's going to be a constant at a particular temperature. So at a particular temperature, we have one portion of molecules that is able to get into the gas phase, and they're going to do that. Remember that if we change the temperature, now in dark blue, if we increase the temperature, we shift our graph. So this one is at higher temperature. If we take a look at that same line, we see that we have a larger proportion of molecules can escape, can become gases. And we're going to see that that's going to therefore increase the vapor pressure. So vapor pressure is dependent on temperature. It is constant at one temperature, but if you change the temperature, your vapor pressure will change. So if your temperature goes up, your vapor pressure goes up. If your temperature goes down, your vapor pressure goes down. And it turns out that when your vapor pressure is equal to the atmospheric pressure, the temperature is the boiling point. So the temperature at which your vapor pressure equals atmospheric pressure is your boiling point. And so that's why we're going to see that water will boil at 100 degrees at sea level. But if you go to Mount Everest, it only boils at about 75 or so degrees Celsius. Not that you would ever go there to just test this out, but it'd probably just, you'd have a hard time coming up with all that, energy to heat that up. So the temperature required for that vapor pressure is going to be your boiling point. Um, and so we're going to say that that is dependent on altitude because pressure is dependent on altitude. So if you are living in Denver, which is got an elevation of what 5,600 feet or something like that, about a mile or so, you're going to see that your water will boil at a lower temperature. On the other side, oh, Tyler's going to go up. The snail is going to climb Mount Everest. Okay, good luck. And he's going to just do some boiling up there. On the other side, pressure cookers work by creating a higher atmospheric pressure within themselves. And that allows your water temperature to increase beyond 100 degrees. So in a pressure cooker, if maybe you have, 1.5 atmospheres or something, you're able to get to higher temperatures and you're able to cook things more quickly that way. So pressure cookers use this idea of vapor pressure to help things to cook more quickly by increasing the temperature of a boiling liquid. So suffice it to say that, therefore, the boiling point depends on your atmospheric pressure, which depends on altitude and other things. So if you go to Death Valley, which is just, a skip away from us, you're below sea level, you have higher pressure. You're going to see that your water would presumably boil at a higher pressure or higher temperature than it would right here in Ridgecrest at 2,000 feet or so. So yeah, exciting stuff. Those of you in Tehachapi are probably going to get slightly, lower boiling water because you're at a higher elevation, right? So there we go. Exciting stuff. All right, one more vocab term for today. Actually, we will probably have more vocab. I lied. Something that is considered volatile in chemistry means it has a high vapor pressure. And this is just kind of, we compare them at one particular temperature. So that if that's at room temperature, we're comparing things that have, relatively high vapor pressures versus ones that have low. So something that would have high vapor pressure would be like gasoline. We know this because gasoline, if you were to spread it out on the ground or something, it's going to evaporate really quickly. We know we can also smell it. Very, as soon as you start pouring your gas, you can smell the gasoline because it is volatile. Whereas for something like cooking oil, you have to get them pretty close to smell it. These are much bigger molecules, stronger intermolecular forces, and they're going to have a low vapor pressure at that particular temperature. Of course, this is all relative. So we're just comparing things. So notice again, this is small intermolecular forces, and this is relatively large intermolecular forces. And so we're going to see that water has a quite magically low vapor pressure for being such a small molecule. Again, just due to those lovely hydrogen bonds that it has. Woohoo. Alrighty, so we have one more bit here to talk about, which is liquid crystals. And then we're done with this chapter, which is awesome. So liquid crystals are an interesting piece of technology. You probably have them in your television or computer monitor or your phone. So liquid crystals are a very interesting kind of thing. They are kind of in between liquid and solid. So they have properties that are kind of in between liquids and solids. And we're going to have a whole different type, a whole different bunch of types of them. Let me see if I can find a nice liquid crystals. Yeah. Okay. So, here we go. Yeah, this is what we're looking for. Okay, so liquid crystals kind of look like this. So these are typically kind of rod-shaped molecules, which are pretty interesting. Um, and so you kind of have several various different ways of looking at these crystals. So they kind of will kind of cluster together in little particles. So they're not quite liquids and they're not quite solids. They're kind of clustered together, but they're kind of not. And so you can kind of see that a true crystal is going to have everything nicely aligned, beautifully in these very regular patterns. And you have different types of liquid crystals that are not as organized, but they still have these clusters of molecules together. So something that is an isotropic one just has these randomly oriented kind of crystal molecules. You have pneumatic crystals. I'm not going to make you memorize any of these words because they're bizarre. These are smectic type A. Try spelling that. These are smectic type C. We're going to see here that smectic type A, they're packed together in kind of layers and they're all pointing vertically. In type C, they're kind of inclined a little bit. You don't need to memorize these at all. But this is kind of what they look like molecularly. Let's see what's this example going to be looking like. So yeah, this is actually a pretty good example. So in pneumatic ones, you do not have, they're all kind of oriented the same way, but they're not in these nice crisp layers. In smectic crystals, you do have the layers. This would be smectic type A, where they're all just vertically aligned. You can have them kind of tilted a little bit. That's smectic type C. Again, don't worry about memorizing that. Not necessary here. And then you have ones that are called cholesteric, which are going to be layers that are kind of at angles to each other. And so all of these have different properties. Let's see if we have some more interesting ones like this. Yeah, so here's kind of the idea. So you have liquids which are just kind of all over the place. You have crystals which are perfectly orderly. And then liquid crystals are kind of in between. So they're semi-orderly. And yeah, so you can kind of just see the idea here is that your molecules, these rod-shaped molecules, just are oriented in different ways. Okay, let's take a look at these just a little bit more. We're going to see that liquid crystals kind of have, yeah, it's kind of like that. It's kind of like that. It's analogous, yeah, we could say that. But it's not really subject to pressure as much. These are temperature based. And so some of them, they'll have a temperature range. Let's say, I'm going to just come up with an example. It's going to be a solid below 40 degrees, and it's going to be a liquid above 75. But in this magic range here, that's where we're going to have a liquid crystal. And if we want to look at molecules that will have this behavior of forming liquid crystals, there's a couple of things that all of them have in common. You typically have something that is a rigid area, and this is done by having either benzene rings or double bonds. And you have some sort of polar bit. And so we're going to see that, for example, if you have something like this, let's even put a triple bond here. This would be an example of a molecule that could form a liquid crystal. So you're going to see that there's kind of two important areas. So I'm going to do these rigid areas in purple. We're going to see that this part of the molecule, the benzene and the multiple bonds there, are going to give it rigidity. And that means it can form the rod shape. So we saw that all of those Google images, the liquid crystals, they were all rods. So having rigidity in it means it can't just flip-flop around and twist and coil. And so you have these rod-shaped molecules. We're also going to see that we're going to have a polar area on them. And that's, in this case, going to be that what's called a carboxylic acid at the end there. And the polar part, these allow the molecules, the rods, to align. So remember that polar things want to be with other polar things. So we're going to see if we had a second of this molecule, we're going to see that it's not going to... Oh, I can't. Maybe I can rotate it. Who knows? But if we had a second one... Oh, gosh. Okay, let's just get rid of this. If we had a second one, it's going to want to align the same way. So it's going to want to align itself so that it can have the polar bits interact with each other. So remember that polar things are... or the dipole-dipole interactions are happy. So we would want our polar parts to be next to each other. And so we're going to see that that's another important component there, if we want them to align together. And then we kind of have just other stuff here. This would just basically kind of change the temperature range. So remember, the more carbons we have, the more our molar mass is, the more our intermolecular forces are going to be, and we're going to see that the more carbons or things that we have there, we're going to have a higher range. So for this random one that I gave you, that was 40 to 75, maybe that's this molecule. If we were to throw 5 more carbons on there, maybe we would boost the range so that it's a liquid crystal in between 90 and 120 degrees Celsius. So it just kind of depends what your application is. And so these liquid crystals that kind of can form these nice layers but still flow around can allow us to do some pretty cool stuff. So, I mean, we're out of time. So I guess tomorrow we will spend 2 minutes talking about properties of liquid crystals, and then we'll start talking about solids. And that'll be our last chapter. So we will probably finish next week, just looking at the schedule here. So we'll finish that next week, maybe Tuesday, maybe Wednesday, we'll see. And then we'll have the entire week after that to review. And then we'll have our final exam the week of the 7th. We'll probably do it on the 7th just because it'll just be similar. Or maybe we can do it the 8th or 9th just because your project is due on the 6th. So I don't want to, have you all spend the 6th cramming to finish that. And then, lo and behold, the 7th is your exam. So that would be not so good. So I'll think about that. But... and we'll choose a date, and we'll have that, and then we'll be done. So yeah. Okay, yeah, well, it'll probably be the 8th or 9th. So we'll worry about that then. So I would definitely spend the week of the 30th focusing on your lab project. So just because we're not going to have any new information there, we're spending that time reviewing. So maybe I can spend some time instead of streaming for you guys. Maybe we could, make scheduled times I can meet with your groups and have a look at what you guys are doing. So, seeing if you're heading the right direction, seeing if stuff is missing. Maybe we can do that instead that week. Maybe have 1 or 2 days of review, and then the other day or two we'll have as time to discuss with your groups or something. So we'll figure that out next week. Alrighty. So with that, I will see you all tomorrow. Alrighty. Take care.